on video analysis. First speaker is Jiangkai Wu. He is a master's student from Peking University, and his research interests include the transmission, reconstruction, and interaction of immersive volumetric video. He'll be presenting ZGaming, Zero-Latency 3D cloud gaming by image prediction, and he's also mentioned this is his first time presenting at the conference, and he's quite excited about it.
Yeah, thank you for introducing. Hello everyone, I'm Jiangkai Wu from Peking University. In this talk, I will present ZGaming, a zero-latency cloud gaming system based on image prediction. First, why do we care about cloud gaming? In cloud gaming, the heavy computation and storage are offloaded to the cloud server, so the client only needs to act as a video player. This enables a thin client, like smartphone, to run complex read games. However, one problem is interactive latency. It's the time between user making an action and the corresponding frame being received on the client device. Obviously, the latency includes at least one round-trip time. So network conditions have a significant impact on the latency. Usually, the latency should be less than 60 milliseconds to obtain the same experience as a local game. But in many cases, it's around 120 milliseconds or larger, so there's a gap. To reduce the latency, we can optimize network conditions to reduce RTT, like congestion control. In those directions, there are many great works. But ZGaming follows another approach. This is, instead of waiting for receiving the real frame from the server, ZGaming responds to user actions with predict frames. In this way, user can be responded immediately and no experience any interactive latency, which means zero latency. The most widely used prediction method is depth image-based rendering, DRBR, which projects the contents from an input frame to a new viewpoint. So in ZGaming, once the user takes an action, the client device can use DRBR to predict the frame under the moved view. We evaluate the potential gain of DRBR. We use PSNR to measure the visual quality. The higher the value, the better the user experience. Yeah, our results show that DRBR can reduce the interactive latency to 0, but leads to a huge drop in visual quality. So this is because DRBR introduces many errors when predicting images. So in ZGaming, the key is to prove the performance of image prediction. Here is an example of prediction errors. We can see there are many missing pixels on the predicted image. This is because the sense contents in those areas were not sampled in the input frames due to reasons like occlusion or out of view. So DRBR cannot project them to the target view, so leaving missing pixels. To reduce the missing pixels, we need to enrich the sense content for DRBR. But where can we get more sense content? We observe that in games, most sense are visited more than once by the user. So we can make full use of the frames in the gaming history to enrich the sense contents. To prove this, we compare DRBR with a single frame and DRBR with multiple history frames. The result indicates that adding the history frames can significantly increase the pixel coverage. In this way, the missing pixels from all covered areas can be reduced. Here is another example of prediction errors. You can see there are many mismatches between the predicted image and the ground truth. This is because DRBR projects contents recorded in the input frame. For static objects, it works well. But for dynamic objects, such as the in-game character, they are always in motion. Their real positions, their poses, and appearance are always changing. So the content recorded in the input frame are already outdated, causing mismatches. We observe that the motion pattern of dynamic objects can be learned from sequence of previous frames. So instead of DIBR, we propose a LSTM model to deal with dynamic objects by inputting the previous 5 frames of a dynamic object. This model can directly predict the next 5 frames in an end-to-end manner. Apart from prediction errors, we found that the selection of bitrate also has an interesting impact on prediction performance. When we selecting the bitrate, existing algorithms tend to increase the bitrate, which may hurt the prediction performance. To prove this, we show the prediction performance on the different visual quality and interactive latency. On one hand, increasing the video bitrate can improve the video quality. So better input frame leads to better prediction performance. But on the other hand, increasing the bitrate potentially leads to an increase in interactive latency, resulting in a longer prediction period, which in turn may hurt the prediction performance. So there is a trade-off between video quality and interactive latency when selecting the bitrate. Moreover, this trade-off should adapt according to user actions. Here is an example. On the left is a gaming recording where the character first walks slowly, then suddenly jumps. On the right is the prediction performance while maintaining zero latency. We observe that when the character walks slowly, the prediction performance is good. During this period, the video quality dominates the prediction performance because even longer-term prediction still works well. So increasing the video bitrate can further improve the prediction performance. But when the character jumps suddenly, prediction becomes difficult. So reducing the bitrate to reduce the interactive latency can make the prediction performance better. So to design an adaptive bitrate algorithm to optimize prediction performance, we take 3 steps. First, based on the current network conditions, we estimate the interactive latency at a given bitrate. Second, based on the latest prediction performance, the estimated interactive latency and the video bitrate, we estimate the prediction performance at the given bitrate. Finally, the bitrate that maximizes the estimated prediction performance will be selected. Next is our evaluation. It's based on real-world recording of a popular 3D game. As for the network settings, we collect network trace from a real-world commercial cloud gaming platform. We compare ZGaming with 2 cloud gaming systems. GameAnywhere is a well-known traditional cloud gaming system without prediction. DRBR-based is the cloud gaming system that uses the original DRBR to predict images. This figure shows the video quality while maintaining zero latency. It indicates that ZGaming can significantly improve the video quality experienced by users. For example, ZGaming's video quality is above 33 dB in 40%, compared with only 4% for GameAnywhere. On the other hand, ZGaming can significantly reduce the probability of user experiencing low video quality. For example, ZGaming has only 3% where the video quality is below 25 dB, while GameAnywhere has 40.4 or 50.5%. To sum up, our vision is using predicting images to respond to user actions immediately, enable a zero latency cloud gaming experience. The key challenge we face is how to prove the quality of predicted images. For this, we propose a history frame cache, an LSTM model, and an ABR algorithm. The evaluation results show that ZGaming can greatly higher video quality experienced by users while maintaining zero latency. Yeah, it's all. Thank you for listening.
Hi, great talk, exciting work. This is Priya from MIT. So from what I understood, ZGaming is using a computation graph based on LSTMs. I have two questions. Where is that LSTM running, and is it real time wherever it's running?
It's a good question. Actually, this paper has a long limitation section. Yeah, because of the time is limited, so I don't mention it. But your question completed my presentation. Thank you. Actually, yeah, cloud gaming clients, maybe a smartphone or browser, they have poor computing power. Yeah, so LSTM has intensive computation, right? So we also offload the computation of LSTM to the server. So in our architecture, for each dynamic objects, we predict multiple future frames for it on the server. Yeah, and the client can prefetch the predicted frames from the server. Yeah, given that the server don't know the actual interactive latency, at the moment the client receives the predicted frame. So the server needs to predict multiple frames so that the client can select the frame match the actual interactive latency to display.
Okay, thank you. Can I ask one more question?
Yeah, go for it as the next speaker gets set up.
Okay. If you're predicting the next frames at the server side, you're not taking into account the input data that the client has. So how are you doing that prediction?
Sorry,
Oh, okay, I'll talk to you offline. Thank you.
Yeah, there's also room in the end for like a panel with all the speakers, so you could ask it then.
Just a quick question here. Just a quick question, yeah. Renata Teixeira from Netflix. I was just wondering what assumptions you have in terms of which kind of games you can use ZGames for?
First, the title is Zero-Latency 3D Cloud Gaming. So first, the game should be 3D game, not 2D games. And our evaluation is conducted on GTA. So.
Yeah. Okay. Thank you. Thank you. As I said, there is a panel in the end. Thank you. The next speaker is Yuan. He's a PhD student from USTC, and he's advised by Professor Jiangkai. His research interests are in mobile intelligent computing and IoT, and he's currently a final year student and looking for a postdoc position. Yeah, over to you.
Okay. Thanks for the session chair Ganesh introduction. Thank you. And hello everyone, my name is Yuan, and this paper I present today is named the PacketGame, and I'm very excited to share this work with all of you in SIGCOMM'. First, I will briefly introduce the background. I think all of us are very familiar with the wide application of video analysis, so I want to just start directly from our own development experience. We have been developing a video analytics system for about 1 year at our university for campus security supports, including the mobility analysis and anomaly detection, this kind of functionalities. And we need to process over 1,000 real-time high-resolution video streams from IP cameras just installed in our campus. And we use an edge server that has 12 CPUs and a Titan X GPU, and we deploy the state-of-the-art object detection model YOLO-X for the object detection, and originally the throughput is 27 FPS. And to optimize the efficiency, we apply several existing techniques. The first one is TensorRT. It's a model acceleration tool, and the optimized YOLO-X model can achieve over 750 FPS throughput. Then we apply Infi. It is a frame filtering technique that proposed in our last year MobiCom paper. And Infi can selectively pass necessary frames to the inference model. Thus, it can further improve the efficiency of the end-to-end pipeline. Notice that the throughput tests are all started from the video frames after decoding. However, when we move to the real system that starts just from 1,000 of the encoded video streams, we found that the end-to-end concurrency is just bottlenecked by the decoder. The reason is quite clear. The decoder needs to process all the frames, while the inference model only needs to process the selected frames passed by the input filter. So, in this work, we propose a new idea, that is to selectively pass video packets to the decoder, and we call it a packet gating task. And compared with existing ideas like the video compression and the frame filtering, model acceleration, our idea packet gating is the first that can reduce both the decoder and the inference model's overheads while supporting commodity cameras and offline videos. Now I introduce the design of our packet gating solution named PacketGame. To selectively pass these packets to the decoder, we need just some quantitative scores for video packets so that we can make some selection. The first available hint we found that is the historical feedback. Here, following previous frame filtering methods, we use a redundancy feedback that checks whether the inference result is just identical to the last result. Then we formulate this task as a multi-armed bandit where each stream just represents an arm. And when some streams are selected, these arms are played. Then we can receive the corresponding rewards without any human labeling, just using the inference result checking. And we set 1 for necessary inference and 0 for redundant inference. It is an exploration and exploitation process. Then we can use the received historical rewards to compute some of the packet scores. And we name this module as the temporal estimator since it captures the temporal pattern. Besides the historical feedback, the packet level metadata is also another available hint for our choice. And we choose to use the packet size and picture type metadata, which can be directly read by the parser without any decoding operations. We divide packet metadata into 2 views according to the picture type, either independent frames or predicted frames. Then we use 2 sequences of the packet sizes in a time window as the inputs, and design a neural network-based predictor. We offline collect pairs of packet metadata and corresponding redundancy label to train this predictor. Now we have the packet scores returned by 2 modules, one from the contextual predictor and another from the temporal estimator. So it's very natural to study how to fuse both of them. We propose to fuse the temporal estimator's output just as another input view of the neural network. Before the fusion, there are 2 input views. One is for the independent frames, another for the predicted frames. And we add the 3rd view and concatenate the score before the last fully connected layer in the neural network. We have now obtained a quantitative score for packets from the various concurrent streams. So it's time to do the cross-stream packet selection. We formulated this problem as a combinatorial optimization problem, and given the scores and decoding costs of packets, we just aim to maximize the summed scores of selected packets under a given decoding budget determined by your hardware. Since the packet decoding costs are dynamic, which depends on the picture types and codec configurations like the GOP sizes, solving this problem is non-trivial. Fortunately, we show that in this paper, this problem can be seen just as an approximately fractional knapsack problem. And we prove the approximation ratio of the greedy algorithm. In practice, such an approximation ratio can give us a more than 95% performance guarantee. Combining all the 3 modules, we present the PacketGame solution. And we prove an overall performance guarantee using the contextual MAB framework. Now it's time to evaluate PacketGame. We use 2 public datasets and 1 dataset collected from our campus from the 1,000 and IP cameras. This dataset covers 3 types to evaluate the generability of our work, including the IP camera, offline video, and the mobile cameras. And we consider 4 different video inference tasks: person counting, anomaly detection, super resolution, and fire detection. And PacketGame's code is open source. First, for the most important part is the overall performance for the concurrency level. We set the target accuracy as 90%. And for the 4 tasks, PacketGame can achieve 2.1 to 4.8 times end-to-end concurrency compared with the original inference pipeline. And we did ablation study to evaluate 2 different modules, one is the temporal estimator, another contextual predictor. And we found that these 2 different module contributions are very different in different tasks. For example, the contextual predictor outperforms the temporal one for the person counting task, while for the super resolution task, the temporal estimator dominates the contribution of the performance. We also tested micro benchmarks, and PacketGame shows very robust effectiveness with respect to involved variables, including the training size and window length and video codecs and so on. If you are interested in details about our design, theoretical analysis, experiments, please read our paper. Here are some take-home messages. First, the system bottleneck for multi-module pipeline is constantly changing. And now, I think it's the decoder's turn for the large-scale video analytics systems. And PacketGame gating is promising and easy to implement. You can try PacketGame for your next video analysis system. And in the future, similar idea, I think, could be explored for packet-level selection of other data modalities, including the audio and wireless signals. I hope to inspire your research. And last but not least, I really need to thank my advisors, Professor Xiang Li and Professor Lan Zhang, for their support and guidance, and thanks for researchers and engineers at IAI for developing our video analytics system at the USTC. Thank you, that's all.
We have time for a couple of questions.
My name is Khalid Diab, HP Labs. Thank you for the talk. So video decoders are stateful machines, eventually. So they maintain state.
Yeah.
But at the same time, you have like different packets from different streams.
Yep.
But you eventually give one stream to the decoder.
Mm-hmm.
So does this mean you refresh the decoding state and lose all the states that you...
We keep the decoding state using the dependency of the different frames. Yeah.
I see. So what about the quality, the quality of the decoded frames? Did you have the chance to actually evaluate the quality of the decoded frames?
I'm sorry?
Like PSNR, for example.
Actually, for different types of the decoder, for example, the B frames and the I frames, we need to maintain the dependency of for one stream. For each stream, we maintain decoding state.
Yes.
Then, for example, we have the budget just for 1 second. If we can decode 1,000 packets, for example, then we can use this budget to select some packets from different streams. For example, if we have 1,000 streams, then we can choose how about 20 or 50 of them to decode the packet.
I see.
Yeah.
Okay, thank you.
Thank you.
Thank you. Any further questions? Yeah, go for it.
Hi, this is Xu from University of Michigan. So I have a question about the overhead. So have you evaluated the overhead or like overall overhead or just like a breakdown of the overhead of the system? Because although the real-time requirements really depends on the specific use cases, but yeah, it'd be good to have this information.
Yeah. That's a great question. Actually, in our paper, we have reported many tested overhead like the latency and the energy cost of our proposed PacketGame, because since it involves some neural network inside it. And I can give you some data. We tested on some embedded system, and the latency involved additionally is just about 10 microseconds, so it's just,
Okay, thank you.
Okay, thank you. Yeah, while Chandan gets set up. The next speaker is Chandan. Chandan is a PhD student. Thank you, Eddie. The next speaker is Chandan. Chandan is a PhD student at Purdue in the Internet Systems Lab. He works on optimization of internet video streaming. He would be on the job market soon, and he is currently in the lookout for internships. So do find him if you like his work.
Hello, everyone. I'm Chandan, and today I'll present Veritas, a framework for answering causal queries from video streaming traces. This work was done at Purdue University. So let's say we want to stream videos, which everybody seems to be doing now these days, and we use a platform, on our platform, Uflix. The quality of the sessions being streamed on Uflix depends on the network conditions associated with these video sessions. Let's say the designers and engineers at Uflix want to improve the performance of these sessions. They are curious and they ask a series of what-if questions. Questions such as, what if we use a different adaptive bitrate algorithm for streaming? Or what if we try to stream higher quality 4K videos? Or what if we try to reduce the buffer sizes for the clients to increase the liveness of video streaming? So how are these questions answered today? Well, one approach is to use trace-driven simulations using the data collected from past video sessions. However, this approach suffers from biases due to hidden confounders in the observed data from past sessions. Another approach is to use randomized control trials, or RCTs, which is the gold standard to answer any kind of what-if questions. However, the RCTs are run on live users, and it can adversely impact the performance for these users. So we should use the RCTs conservatively. So how do we solve this problem? What are our contributions? Well, we present Veritas, a framework for accurately answering what-if questions without using RCTs. We focus primarily on video streaming. We provide a principled framework to tackle causal reasoning, which is reasoning about interventions or changes to a system and answering the associated what-if questions. We simplify this complex task by leveraging domain-specific insights. We show that Veritas achieves much higher accuracy than a widely used baseline approach and a causal sim, a recent causal inference approach from NSDI 2023, which needs RCT training data. Since we are focused on video streaming, let's look at some of the challenges for causal inference in video streaming. First, the network bandwidth associated with the video sessions being streamed is a confounder. We take an adaptive bitrate algorithm and stream video session in varying network conditions. We observe a non-monotonic relationship between the download time of the chunks in the video sessions and the chunk sizes. This is because the adaptive bitrate algorithm would pick higher qualities when the network conditions are good, resulting in smaller download times for the larger chunks and inversely for the smaller chunks. We also see that the TCP state in these sessions could be a confounder. We take a constant network bandwidth emulation environment and send payloads of varying sizes. We observe that the payloads with small sizes could have throughput much lower than the network bandwidth. This is because the observed throughput depends on the size of the payload as well as the TCP state at the start of sending these payloads. Finally, in video streaming, we also have this notion of cascading effects. Let's say we are streaming a session and we know the underlying intrinsic network bandwidth associated with this session. This bandwidth can change extremely over time. So let's say for this session, we have the deployment logs, which highlights the chunk sizes and the associated bit rate for each of the chunk in the session. During our what-if analysis, which we don't know, but let's say we knew, we might choose a different bit rate for one of these chunks, let's say the first chunk. This single change will result in new decisions or different decisions for each of the succeeding chunks, and we might choose a bit rate which is different from the deployed bit rate. But because of the underlying network conditions which would be different for the succeeding chunks, the properties will be impacted. And this is what could lead to some cascading effects in video streaming. So these are some of the challenges for causal inference in video streaming. So let's try to model video streaming and see if we can try to find a solution for this. So in particular, let's start by looking at a chunk in a video session. For this session, when we are downloading or after we have downloaded, we'll have different observed variables associated with it. For example, the buffer size at the start and end of download chunk download, the chunk size, the download time, and the observed throughput for this chunk. We will have all these variables for all the preceding chunks in the session. So our goal is to infer the intrinsic network bandwidth, which is hidden for this particular session and associated with all these chunks. However, it is hidden, and it is a very complicated task, as we can see from this complex causal graph between these variables, which associates the dependencies between these variables. So this inference task is very hard. This is where Veritas makes a crucial decision to observe the TCP state, which is hidden, and simplify the task of causal inference. This key insight will make us infer the hidden network bandwidth much easily. In particular, it satisfies the deseparation criterion between the different variables and will help us to allow us to infer the network bandwidth. This insight helps us to model the relationship between the network bandwidth and the observed throughput using a Markov model. And our Markov model has multiple variables as the hidden state and the observed throughput as the observed variable. More details about the Markov model are shared in the paper. One crucial element is the custom domain-specific emission model, which is different from a generic probability distribution which we use for a Markov model. And this specific domain process will relate the hidden states and the observed variable. So let's look how all of this comes together and we are able to answer the causal queries. So we start with some deployed user logs. We had some setting, and we collected the logs from users, and we want to understand what was the underlying network bandwidth associated with these sessions. So we send these logs to Veritas, which will try to sample the network capacity associated with each of these sessions. Here, it's very important to note that Veritas will provide multiple samples for each user session. And providing multiple samples for a single session is important to account for the inherent uncertainty in the inference approach. Using these network samples, we can then emulate them to answer multiple questions and get the answers for our queries. So let's look at Veritas in action. In this particular example, I just have a trace which we emulated and have the true network bandwidth for this trace. And then we emulate a video session using this trace. For this video session, we have an observed throughput for all the chunks, which is what a generally used baseline would estimate as the network bandwidth, which we can see is it's very low and conservative in its estimation. It's nowhere close to the true network bandwidth. However, when we try to sample the network bandwidth using Veritas, we have multiple samples to account for the uncertainty, all of which are much closer to the true network bandwidth. So we can see that Veritas does make good estimation of the true network bandwidth. So now, can we use Veritas to answer the what-if questions? So in our paper, we have tried to answer multiple questions, but here I'll take an example where we try to change the qualities which we had streamed from low quality to high quality for a video, and then see if Veritas can help us answer this question of how the distribution of the quality matrix for different sessions would look like. So in this slide, this is what the ground truth would look like. Like if we had streamed higher quality videos, what would be the average quality of the sessions or the rebuffering ratio for these sessions? Our goal is to be as close as possible to this ground truth values. And that is indeed the case when we use the Veritas samples and try to ask this question. The Veritas distribution is much closer to the ground truth compared to the baseline. We also compare Veritas with a very recent approach, Causal SIM. Let me talk more about this. So Causal SIM requires RCT training data, whereas Veritas has no such requirement. What I mean is, to infer the performance of a new ABR algorithm, the Causal SIM would require RCT data from at least 2 ABR algorithms. However, Veritas has no such requirement. Further, it would be difficult to answer questions which are outside the scope of the initial RCT experiment using Causal SIM, whereas Veritas can answer a wider range of causal questions. We run the same question as before, which was about changing the video qualities, and we see that, again, Causal SIM is not close enough to the ground truth values, whereas Veritas, as we saw before, is closer. Let me wrap up by providing the key highlights from our paper. We provide a novel framework for causal inference without using RCT data. We answer a wide range of causal queries using both emulation and real-world validations, details of which are shared in the paper. We have shared our artifact on GitHub. Thank you everyone for listening, and please let me know if you have any questions. Thank you.
Thank you. Very exciting work. Exciting to see causality taking off in this field. In the Causal SIM paper, there's this case study about comparing the Pareto frontiers of BBA and BOLA. That's a really interesting experiment. Do you have any insights to share on Veritas in that experiment?
So inferring the, so how we compare the performance of BBR and BOLA, or okay, so is the question like, can we infer the performance of a new ABR using Veritas?
I mean, that's what a simulator does, but like that case study is about, let's see how Causal SIM and how some other thing, something called Expert SIM compares BBA and BOLA one. According to the parameters that they have, the hyperparameters, creates a Pareto frontier and says, okay, this one is better than that one. The interesting thing there was that the Expert SIM and Causal SIM were completely against one another.
Yes.
That's what I'm asking.
Yes. We do an experiment where we try to see if we can learn like a different ABR algorithm, and we have some results in the paper. We do have done this experiment in my understanding, but we can discuss more in detail.
Okay, I'd love to read that. Thank you.
Yes.
Hello, Alexander from ETH Zurich. My question may be a little bit of a follow-up to your answer. So it seems like Veritas is very good at estimating or modeling the network state. Could that be the basis for an ABR algorithm itself, kind of using this kind of model to make the next decision for the next chunk?
Yes, that's a great question. So what I was showing today were more about counterfactual queries, but if we want to use to improve an ABR algorithm in the real world, that would be an inference task. We had done a few experiments for that, but we could not complete them, but it is definitely possible. Like, it can be integrated to make decisions for an ABR algorithm.
Thank you.
Let's thank the speaker. Thank you. Last talk in this session is by Bruce. It'll be on Sammy smoothing video traffic. Bruce finished his PhD recently with Nick McQueen, and while he's currently sort of like taking a break, he would be joining Netflix very soon. So,
thank you. So I'm excited today to present some joint work between Netflix and Stanford. So our work is looking at streaming video traffic, which is the vast majority of traffic on the internet today, somewhere between 65 and 76% of all the bits sent online. Our goal in this paper is to do something to video traffic to make it friendlier, to improve the performance of neighboring traffic that shares the same networks, maybe by increasing their throughput, reducing their queuing delay, or their packet loss. One of the reasons that Netflix is interested in this is if we can improve the performance for all neighbors, we can improve the performance for video itself. Because video is such a large fraction of the internet, it probably shares the network with itself in many places. So not to spoil our results too much, but one of the more surprising results is we're able to reduce the peak throughput for Netflix by more than 60% without reducing the performance of video itself. So this is sort of a surprising result because we think about congestion control and throughput. We think about throughput as the domain of congestion control algorithms, which have kind of nailed down sharing by now. So we have this server, which is sending data to a TV, and it does this by picking a throughput over time. And there's sort of two competing goals here. One is to fully utilize the network and send as quickly as possible, and the other is to fairly share the network with neighbors. So maybe we wind up with a throughput trace that looks something like this, where we send fast for a while, and then we dip down, and then we send fast again. The problem, though, is that we might have a throughput which is too low, and so the video might rebuffer. To deal with this, the industry has developed adaptive bitrate, or ABR algorithms. We take our video, we split our video up into few-second chunks, and we encode those chunks at a range of different bit rates. The ABR algorithm will go chunk by chunk, and it picks a different bit rate for each chunk. So here, maybe we start with a good-looking video, we switch down to a bad-looking video, we switch back up to a good-looking video, and this lets us avoid the rebuffer, but at the cost of quality. In general, ABR algorithms optimize for quality of experience, or QoE, which is a trade-off between bitrate, rebuffers, and play delay. So the challenge with this sort of setup is it seems like if we did something to make the traffic friendlier to neighbors, we would wind up making video traffic worse. So like maybe we give up some throughput here to a neighbor, but what this means is we get lower video bitrate down here. So one of the main things I want you to take away from this talk is that this is maybe the wrong way of thinking about video traffic today. We can actually make video traffic friendlier, and we can do so with the same QoE as today's top production algorithms. As a consequence, our work suggests there's a lot of improvement for congestion control if we look at what the application needs to perform well instead of the underlying details of the network. So the big observation that lets us make progress here is that video is not usually limited by throughput. So there are sort of two trends that have been helping with this. One is that ISPs around the world have invested in faster and faster networks, so throughputs have gone up, while at the same time, large video streaming services have invested in more and more efficient bit rates. And so bit rates have not grown as fast as networks. And so here's some data. This is from Netflix for TVs. The average Netflix throughput is about 13 times higher than the video bitrate. So there's a lot of extra throughput here to go around. Because of this, when we zoom into a single video session, video is actually very bursty. It has what's called on-off behavior. This is because the throughput for video is actually controlled at 2 different timescales. In the short term, we have congestion control, which is trying to send as fast as possible during these on periods. But over the entire duration of the video, the long-term average throughput must just by definition be equal to the video bitrate, because we're downloading some number of bits over the duration of the video. And so because of this, we wind up with these long off periods of silence where we don't send anything at all. And this reduces the average throughput down to the bitrate. So our goal in this paper is to get rid of this behavior, to smooth out video traffic like you can see here on the right by reducing throughput during on periods. There are sort of 2 benefits to this. So over on the left, the video is sending quickly, TCP is blasting away, maybe we get a little bit of queuing delay, a little bit of packet loss. Over on the right, we're sending so far below the capacity of the network, we're actually going to avoid that sort of congestion completely. The other benefit is to neighboring traffic. So imagine you're, say, Zoom or gaming or some other streaming video. Over on the left, you have to compete with video traffic in these sort of unpredictable on periods. But over on the right, you have this very consistent, very smooth, available bandwidth that you can use for your own performance. There's been a whole bunch of work smoothing out video traffic. The big difference with our paper is that we do it without reducing the QoE of video itself. So now let me tell you about our algorithm. Our algorithm is called Sammy. It's actually named after the world's fastest snail, which is, you can see up here at the top. We're sort of slowing things down, smoothing things out, but it still works well. So we introduce a mechanism to smooth out video traffic. It's called application-informed pacing. Basically, the ABR algorithm picks a chunk. It also picks a pace rate. It sends that to the server, and the server doesn't send faster than that pace rate. So here, the TV picks 2 megabits per second. It sends it to the server. The server doesn't send faster than 2 megabits per second. This is just like your typical TCP pacing, with one crucial difference, which is that the pace rate is picked by the ABR algorithm and not the congestion control algorithm. One thing I want to highlight about this mechanism is it's super deployable. So I'm going to tell you about experiments we ran in production at Netflix. We have an open source demo which uses the Fastly content delivery network. Probably other content delivery networks also work. And it's pretty easy to implement in an existing web server in Linux. It's just a couple of lines of code. So the real challenge here is how does the ABR pick the pace rate? This is real interesting. We got a whole bunch of pages in the paper about this. We got theorems. But here the key idea. We take our ABR algorithm, we figure out the throughput it requires to pick the highest bit rate, and we pick a pace rate which is just a little bit higher than that. So in our experiments, we're going to do about 3.5 times the video bit rate when the video buffer is empty, and about 2.5 when the buffer is full. So this is certainly still above the video bitrate. We're not smoothing things out perfectly, but remember that the average is 13 times higher, so we're really going to be decreasing things over what we do today. Let's look at what this does in the lab. So here's an existing Netflix session. It runs TCP Reno. It's a 40 megabit per second link. You can see it keeping the link full at the beginning, and then it switches to on-off behavior later on. When we look at the round trip time is elevated because TCP Reno is keeping the queues full. So we can compare this to Sammy, and Sammy's going to look very different. So you can see right when the video starts playing at about 3 seconds, Sammy decreases the throughput by half, and then it continues decreasing throughput over the rest of the video session, down to about 1/4 of the capacity of the network. Because this is so far below capacity, when we look at the round trip time, there's no queuing delay at all when Sammy is running. So next we look at how this impacts some neighboring traffic. We run a UDP session. UDP doesn't see any queuing delay. It actually sees a 51% lower round trip time. This is because Sammy is not filling up the queue. For a neighboring TCP session, that session actually gets 28% higher throughput. This is because here in this link, the fair share is 20 megabits per second, and Sammy is sending slower than 20 megabits per second, so there's some throughput available. We also run lab experiments with HTTP requests, where the response time improves by 18%, and also neighboring Netflix video sessions, where the play delay improves by 4%. So this last one is particularly exciting because it means video services are incentivized to deploy Sammy when they share the network with themselves. So now let me tell you about some large-scale randomized experiments we ran with Sammy at Netflix. So Sammy reduces congestion-related metrics. We saw a 62% reduction in instantaneous throughput. This is a good thing. We saw a 50% reduction in retransmissions, and we saw a 19% reduction in round-trip times. All of this did not come at a cost to QoE. We actually saw very slight improvements in QoE. And you can, if you want to know more, you can see the paper. So Sammy reduces congestion, but it's a bit weird for congestion control work, and I wanted to end by talking about this. So with your typical congestion control algorithm, the goal is to work for all kinds of traffic. This is a hard problem, and to do this, we need some assumptions. And so we assume that applications benefit from the highest instantaneous throughput they can get. Because of this, we think about things as sort of a zero-sum game, where we can't make our neighbors better because we'll make ourselves worse. With Sammy instead, we're looking at one specific goal, which is to stream video. But remember that this is the majority of traffic on the internet today. For video, we don't need these assumptions. We just know what it needs to perform well, which is that it needs good QoE. And so because of this, we wind up with different goals. We actually try to minimize instantaneous throughput here. This is like the opposite direction we normally try for in congestion control, and we reduce throughput by 60%. We also show that we're not really in a zero-sum game here. We can give up throughput to neighbors. It doesn't hurt the QoE of video, and it improves the performance of those neighbors. And so because of this, I'd like to encourage us as a community to think about how we can make our internet applications friendlier. There's a lot more we can do for streaming video. This is, I think, very just a start. There's also a lot of other applications that use the internet, Zoom and web browsing and gaming, and we can do things to make those applications friendlier too. So Netflix is interested in this sort of work because it has benefits to Netflix. I think all large streaming services would be interested in this because it benefits them. But more generally, it benefits all of the traffic on the internet, and it benefits you and I when we use the internet and we share it with video. And so with that, I can end and I can take some questions. Thank you.
Hi, great talk. I'm Udit Paul from UCSB. So I was wondering, this clearly works really well where like you have good enough throughput, like 40 Mbps and what you showed us. I was wondering how it works for areas where throughput itself is a problem, and what your opinion might be in terms of how Sammy would work in those scenarios.
Yeah, so we started here. This is a great question. Looking at networks where the throughput is so much higher than the bitrate. And remember, this was the usual case for most traffic on the internet. It's a much harder problem if you're constrained by throughput, and then I think you're back a little bit more in the zero-sum sort of universe, where if you give some throughput, it immediately goes to another application. But I suspect there's stuff you can do to be friendly as well. Maybe you can smooth things out over a shorter time scale or something like that.
Hi, Julian from UC Berkeley. I have a question. Maybe this was already covered, and I'm sorry about that, but how would you do this for Zoom? Since Zoom doesn't buffer anything, it's instantaneous, you can't really smooth it out. Would you have a solution to do this for Zoom?
I have actually not thought about Zoom at all. Yeah, I think it's a wide open question and it's super interesting.
Okay, cool. Thanks.
Yeah.
Thank you for a great talk. My name is Roman. Would this technique be working for wireless networks or just for wired?
So this will work for any network where the throughput of the network is higher than the bitrate of the video. And so to the extent that that's true in wireless networks, it will work in those networks too. Yeah, but often, wireless networks are a bit slower, and so maybe this would less commonly work in those networks.
Hi, great talk. I'm Xiaojing from Yale. I think Sammy is more suitable for the continuous video stream, but I wonder, can you share your opinion about the application in short videos like TikToks or?
Yeah, it's another great question, and again, we've thought mostly about long streaming video, because again, this is most of the traffic on the internet. I think the big theme here, though, is like if you think about what the application really needs, maybe you can sort of exploit that to make it friendlier. And it seems entirely possible you could do that with TikTok, too.
Let's thank the speaker. I'd like to just have maybe all the presenters we have time, few minutes for like a brief panel in case there are more questions or questions that are, targeted at multiple of these works. So, yeah. You have a question?
Can I? Yeah. Sure. Yeah. Actually, I have a question for ZGaming, and I'm curious about how well can your neural network, I think you use the LSTM-based model, how well can it generalize? How many are, what's the ratio of the training samples you need required to train an effective network?
Yeah. Actually, we first train a model, and for a new game, we need to fine-tune. So maybe we need to train a model for each game. There may be domain gap between different games. Yeah. So if your neural networks is general.
Yeah, actually, I leverage a neural network-based model, and for me, the generability is we can use just, for example, 10 cameras installed in our campus, and to generalize it to 1,000 cameras, it can generalize to this kind of scale.
General to campus.
Yeah, to different cameras. Yeah.
But what if a new campus?
I have not a new test bed for that. Yeah, sorry.
It's great.
Any further questions from the audience? I had one for Sammy, which was that when you pitched it to Netflix, was there a thing that said, hey, we could reduce our throughput but keep the QoE? Was there a pushback that said, why can't we, keep the throughput and increase our QoE instead? What's the point of, why are they interested in being nice?
Yeah, totally. I think the big benefit for services like Netflix is they're so big, they probably share the internet with themselves in many networks. And so, you can be like, oh, we could increase the throughput, we can increase the QoE, but it's sort of hard to believe that you would also not hurt yourself in the process.
I also had another question targeted at both PacketGame and ZGaming. Both of it involved a little bit of, sort of like a prediction, so to speak, at a high level. How do you deal with, rapidly evolving video? Like when the video content or the scene changes dramatically, how does your predictors and all that, how do you keep up with it? Do you do any sort of continuous learning or any thoughts on those?
Sorry,
So when your video content changes dramatically, like the scene, for whatever reason, the people changes and so forth, does that affect the performance of your system in any way?
Yeah, actually, for sudden actions, such as sudden jump, Yeah, the LSTM is weak to respond to such sudden actions. Yeah, because the architecture of my LSTM model is inputting previous 5 frames and predicting the next 5 frames. So the actions last less than 5 frames are difficult to predict. It's a limitation written in the paper.
I had the same question for PacketGame.
For me, actually we have tried some online learning and continuous learning method for this, but I think my best of practice experience is that it's better to connect just enough frames. Like for us, we connect the frames from the day and the night, and from the weekday and weekend, and that is just enough for our application on a campus. And since for the efficiency, we just to transform the learning-based module into a optimized binary running code for the runtime efficiency. So it's if you enable the online learning function, it will hurt the efficiency of the.
There's a question. One question. Yeah.
Hi, glad to see Netflix is taming down the video bursts. I have a concern about this is Yuan Chen from Google. If we just instruct the video with a specific rate, what if it disagree with the congestion control? Like congestion control thinks there is far sufficient bandwidth to pace that.
Mm-hmm. Yeah, so the way it works is the rate which is chosen by the ABR algorithm is an upper limit on the pace rate. And so if the congestion control algorithm wanted to pick a lower rate, then it can go ahead and it can do that. And this, we think, helps it sort of fairly share the network in like a TCP sense. But if the congestion control thinks it can send way faster and the ABR algorithm doesn't want it to send any faster, then it doesn't.
Okay, thanks.
Yeah. Okay. We are at time. Let's end the session. Let's thank all the speakers. Thank you.